In this video, we're going to have a walk through the circuitry of this Softrock Ensemble 2 receiver. It's a software-defined receiver, and really just a two-page schematic here. And we'll go through that in detail and take a look at each of the circuits and how they operate. It might make sense, before we do that, to take a look at the block diagram and describe what is going on in the receiver. Okay, the Softrock Ensemble 2 software-defined receiver can be thought of really as a direct conversion receiver with two identical outputs that are shifted in phase by 90 degrees. And we can kind of see that in the basic block diagram of the RF path here. RF comes in through the antenna, goes through one of four selected bandpass filters into a mixer. The mixer is fed with a clock that is equal to the desired receive frequency, and then the baseband signal comes out here. Now, this is a little bit of a special mixer. It's actually called a Quadrature sampling detector, or QSD, and we'll talk more about that in detail later. But the idea is you feed that with two clocks at the same frequency but 90 degrees out of phase, and you can get out of that essentially two outputs, two baseband outputs that are identical but shifted in by 90 degrees. And these are the signals that are then processed by the sound card and software in the computer to do the final frequency selection and demodulation. The rest of the circuitry here is involved with controlling the bandpass filters and the clock. So these Quadrature clocks are generated by this divide by 4 with Quadrature outputs. We'll talk a bit more about how that's designed. The Softrock is designed that you can populate it two ways, or build it two ways. One is a LF receiver from like 180 kilohertz to 3 megahertz, or as an HF receiver from 1.8 megahertz to 30 megahertz. If you're going to do the latter for HF, which is what I did, you basically bypass this optional divide by 4 with a jumper, and that's what I did on the board that I built here. So the clock that's being generated by this programmable crystal oscillator, it runs at essentially 4 times my desired receive frequency. Again, if you did the LF version, it would be 16 times. That programmable clock generator is programmed through a little I2C bus, a 2-wire digital bus, from the microcontroller. So the microcontroller will get commands from the USB to tell it what frequency to tune to. That will adjust the Si570 output frequency and select the appropriate filter. The rest of the processing is done in the receiver, in the software in the computer, looking at the I and Q signals and doing the final demodulation. So that's the basic block diagram. Let's start walking through the schematic and doing some tests just to kind of show what the signals look like at these various stages. One more thing I want to mention here on the block diagram is you see this dashed line here. And that dashed line is indicating in the schematic here that there are two different power supply domains that are being used here. All of the digital interface for the USB to control the microcontroller and to generate the clock is all powered off of the USB port from the laptop. And that provides sufficient power for this, but also might be a little bit noisy. Plus you also run the risk of ground loops between the USB ground and the sound card inputs here. So we essentially create a boundary. These are galvanically isolated, meaning that there's no DC connection at all between the two. So there's a local 3.3 volt regulator to provide the 3.3 volts for the Si570. The microcontroller is driven off the 5 volts of the USB power supply. But how do we cross this boundary when there's no ground or a power supply in common? It's actually done two ways, and we'll see that in the schematic. Optocouplers are used to transfer signals across this boundary here for these control lines to control which bandpass filter is being used. Because these are just static lines. One's going to be high or low to select which of the 4 switch positions to select the appropriate filter. So those are simple optocouplers that are used there. The RF signal from this local oscillator, it just simply goes through an RF transformer to cross this boundary. So we'll see those on the schematic as we go through. Okay, we'll have a look at page 1 of the schematic. Up in the upper corner here is the analog supply voltage for the receiver, the analog receiver portion of the circuit. Our 12 volts coming in, a reverse protection diode into a simple linear 5 volt converter to create our 5 volts DC to power up most of the analog circuitry. Okay. Now separate from that is this circuit down here. Here's our USB interface to the computer, and that's going off to the Atmel AT-Tiny85 microcontroller, and it's again is doing two things. It is sending out these two signals here out to these optocouplers, and those create our filter select signals. That's FL select 1, FL select 2, or assuming 0 and 1. They go off to the switches to determine which filter we're going to use. It also is sending two signal lines up to this guy, which is the Si570. He's the programmable clock oscillator, and he's programmed through an I2C bus, or I2C, and those are the two pins here. So it gets commands through that bus to tell this device what frequency to create, and its output comes out through this capacitor in through this transformer. So we cross that galvanic boundary there, and that's how we get from essentially our digital power supply domain to our analog power domain on the other side of this transformer and these optocouplers. Okay, here on the board, this is the microcontroller here. These are those two optocouplers right here, and this is the RF transformer that takes the output from the Si570, which is on the back side of the board, and brings it over into the rest of the analog receiver. Now the way this board is set up is that just about all of the integrated circuits, with the exception of the microcontroller, are surface mount devices that are on the back of the board. And possibly later on when we go do some of the measurements, we'll have the board flipped over so we can see that. Okay, so the first thing we've got instrumented here is I have some digital probes probing the I2C pins here and here, as well as the USB pins coming off of the USB connector here. And if you watch carefully on the scope, as I change the frequency that we want to program, we can kind of see the data changing on the scope there as I flip back and forth. What we're looking at on the scope here are the two buses. We have the I2C bus and we have the USB bus. And we're decoding each of those. And if I zoom in, what we're looking at right here, we're zooming in on this portion of the waveform, and this is some data from the USB bus. We can see that it's sending some commands and some data to the microcontroller. And if we zoom out a little bit, what we're looking at down here is the I2C bus. The I2C bus, we can see the two lines for that and the bus decode. That's actually telling them the Si570 to tune to a new frequency. Okay, so let's take a closer look at the tuning behavior of that Si570. So I removed the USB bus. I'm just looking at the I2C bus here now. I can see the bus signals for the clock and the data line. I can see the decode of it here, and we're not going to take the time to go analyze that decode. But let's go probe that clock signal and take a look at the clock and how it changes when we tell it to tune to a new frequency. So I'm going to probe at the output of the transformer and go tell it to tune to a new frequency, and we can actually see that happening. So if we look carefully, I can actually see a change in kind of the color, if you will, of that high frequency clock, and that's actually changing in frequency. If we zoom in on it, we can actually go see that. So if we just zoom in, let's go zoom in on that area where we see the change. It's right about here. Let's just zoom in on that and center it back up on that a little bit. Okay, and now very easily we can see the change in frequency from here down, and we'll go the other way to here. We went from a lower frequency to a higher frequency. So, and that was all in response to this bus command telling it to tune to a frequency. Now, of course, the data sheet for the Si570 will have all the details of what registers you need to program to execute a given frequency output from that device. But that just shows, kind of the cause and effect relationship between the I2C bus and the Si570 output. Okay, we've seen how the high frequency clock is generated by the Si570, goes through this transformer, and then goes into the clock dividers. These dividers are what create the quadrature clocks that are used by the Quadrature sampling detector. This is the optional divide by 4, and it really is just two divide by 2s kind of cascaded. A simple D flip-flop with the inverting output fed back to the D input will divide a clock frequency by 2. So we do that twice, and that would be the divide by 4. Since we built this as the HF version, we didn't populate this chip, and we populated this jumper, which brings us down to this block down here, which is also a divide by 4 that gives us two outputs. And these two outputs are the clock frequency divided by 4, but each of these outputs is shifted by 90 degrees, or a quarter of a cycle. So let's take a look at how this circuit works, and we'll take a look at some of the waveforms. There's a simplified schematic of that Quadrature clock generator. So our high frequency clock comes in here, and I've drawn essentially a timing diagram of that here. And this is the way the two D flip-flops are connected. The inverting, or the inverted output of the first D flip-flop is connected as the input to the second, and the non-inverting output is cross-connected back to the first. So let's take a look at how this works. Let's assume that we're starting off with both flip-flops cleared, so this output would be low and high, low and high. So that's kind of indicated by these waveforms here for Q and Q bar, Q and Q bar. So these two are low, low and high, low and high. At this first clock edge that's applied to both flip-flops, we could take a look at what happens at each input. So when this goes high, what is this guy doing? This guy is already sitting low, so that's not going to change on that clock edge. So that continues on. The outputs only change on the rising edge. Now let's look at what happens with this flip-flop. When this input goes high, the D input is coming from here, so that output is high. So this output is then going to flip. Okay, so essentially this low level here gets transferred up there, this high level gets transferred down there. Now at the next rising edge, we do the same thing. This state changes now because that's going to be looking at this high output that's coming from the Q bar, so that changes state. Okay, but this guy is sitting already high, so that doesn't change state. So we can continue to the next clock cycle, and if you look through it, you can kind of see how the whole thing works. So what you wind up with is a clock, signal here that is 1/4 of this frequency, and the same thing down here. But if you look at these two, they are shifted by a quarter of a clock cycle. So the two clocks that we're going to use in the circuit are this one here. We'll call this clock I for the in-phase clock, and this one is clock Q for the quadrature clock. And we can see that the quadrature clock follows by 90 degrees. So we say this edge is 0, then that edge goes a quarter of a cycle later, then this comes down and that comes down. So there's our quadrature clocks and how they're generated in the flip-flops. Okay, to look at the quadrature clocks, we need and all three of the signals of interest, I need to hold 3 probes down here, so see if I can do that. So now we can see on the scope screen, the top trace is the higher frequency clock that's coming directly from the synthesizer, and then the two clocks below, the cyan and the purple, channels 2 and 3, are my in-phase and quadrature clocks. And if you look carefully at them, you can see that each of the quadrature clocks is 1/4 of the frequency of the input clock, and that they are shifted 90 degrees, or a quarter of a cycle, with respect to each other. So it's these quadrature clocks that are now applied to the quadrature sampling detector to create the IQ outputs for the receiver. Before we get into the quadrature sampling detector, let's first take a look at the switched bandpass filters. So these are the filters here. For the HF version of the radio like I built, they're basically going to be 1.8 to 4 megahertz, and then 4 to 8 megahertz, 8 to 16 megahertz, and 16 to 30 megahertz. The two lower frequency bands include a little bit of an attenuator up front for the typically larger signals that are seen at those bands. So let's go take a quick look at, make sure we're getting proper band switching. Okay, to take a quick look at the bandpass filter characteristics, I'm putting a high frequency random noise signal, or a white noise source, into the front end of the receiver, and And that's going to give us a relatively flat noise power across at least 50 megahertz or a little bit more. So that's going into the input. We'll switch the receiver to operate at a frequency in each of those 4 bands, and take a look at the output of the filters right here, just on the spectrum analyzer. Now, where I'm probing it is very close to the clock, so I'm going to pick up some clock feed through. There's going to be a little bit of clock feed through here, so I'm not too worried about that. You'll see that. So right now, if I touch the probe down here, we're looking at, that's the bandpass characteristic for the high-pass filter, the highest frequency filter, which is the 16 to 30 megahertz filter. We're looking at a span from about DC, a little above DC, out to 50 megahertz. So if I look down at the next band, that one should cover from 8 to 16 megahertz. You can see that filter shape change there, and I start to see the various clock harmonics there, and I kind of expect to see that. The next band down is 4 to 8 megahertz, and we'll see that down there. We see the whole noise floor drop because we're going through the attenuator in that case, but I can see that bandpass characteristic right there, and I'll put the probe back on there and switch to the lowest frequency, and you can see the filter shape change down there. And of course I can see the clock feed through that I'm picking up off the board here. I'm not too worried about that, but I'm seeing the proper filter shapes as I cycle through these various filters. So we know that part of the circuit is working properly. Now, those filters are switched in by these little dual 1 to 4 demux and mux selector switches, and you can think of these as a pair of it's really a double pole 4-throw switch, and so like the 1A will connect to these 1B outputs 1, 2, 3, and 4, depending on the state of the switch inputs coming in, the filter select lines coming in here, S0 and S1. Similarly, the input number 2 on the A side will switch to outputs number 2 on the B side, 1, 2, 3, and 4. Okay, so really the selection of these 2 bits here will determine which of the 4 outputs each of those go to. So this chip is used in 2 places in this design. It's used here to switch the various filter paths, and it's also used down here in the Quadrature sampling detector circuit. And we'll take a look at that in more detail. Okay, the bandpass filtered RF signal then comes out and goes down through this transformer that basically creates 2 copies essentially of the RF signal that are 180 degrees out of phase. So kind of have RF and RF bar, if you will, down here, so more of a balanced output. That balanced output then goes into another one of those CMOS switches, and this is configured to perform the Quadrature sampling detector. You can also think of it as a Quadrature mixer, and it's also known as a Tayloe detector, after Dan Tayloe, who invented this circuit architecture and actually patented it. To understand how that detector works, it helps to draw a little bit of a simplified schematic. So let's look at that. Now, the original design that Dan put together for the Tayloe detector was really a switch that would switch between one of 4 outputs, so like a single pole 4-throw switch that would run at 4 times the clock sampling rate. So the design that's used here implements the same thing, but does it just a little bit differently. And so really what we have is 2 single pole double throw switches, and then the position of those switches is controlled by those 2 clock inputs. Okay, and they kind of run through this process here. So we can kind of say, well, when both those clock inputs are at their low level, we'll call that the first quarter phase, or 0. And the output that gets selected is 1. So we're going to connect the RF to the I output where it gets integrated. And then the next phase at 90, clock I goes high, clock Q is 0, the output that's selected is 3, and that's here. So we're going to connect the RF output again to Q. And then the next 2 phases, 180 and 270, are going to connect the inverted RF to I, then the inverted RF to Q. So the way you can think about that is, let's say we're sampling this sine wave, this maybe the RF carrier we want to detect and demodulate. So we're going to be essentially, during that first phase, sending this signal to the I integrator. Then the next clock phase we send this signal to the Q integrator. The next phase we send this signal, but it's not really this signal because remember we're sending RF bar, so it's really the mirror image of this signal. If I can draw that on camera. That mirror image is getting sent to I. You'll notice that signal and this signal are the same, so they essentially just add up. We get a nice gain out of this detector from that standpoint. And then the last phase we send this signal to Q. You'll notice that if the sampling clock, these switches, are exactly 4 times the signal we're looking at, what we're going to effectively get out of the I and Q outputs are DC. And that's essentially why this is a direct conversion receiver. We're going to take the signal that equals our desired frequency and convert it essentially to baseband right to DC. Now if there is any frequency offset between the clock frequency and the signal of interest that we're looking at, the outputs of I and Q will be sinusoidal, and the frequency of that sinusoid will be equal to the frequency difference between our desired frequency, the actual center, and the actual frequency coming in. So we use that fact to actually go test the Quadrature sampling detector to be sure that it's working. Now the I and Q outputs from the Quadrature sampling detector are essentially integrated or low-pass filtered. The I and the Q signals both go into essentially being filtered by this capacitor here, and then through a simple op-amp filter here and here, and those outputs go out to the jack that goes out to the audio input of your computer that does the final frequency selection and demodulation. So I'm going to probe on the board these 2 resistors here, and with the signal coming in, and we'll go take a look to be sure that the rest of the circuit is working. So down here on the board, I'm probing those 2 resistors, which are essentially going right to the line output that goes into the sound card. I've got the input to the receiver being driven by a sine wave, unmodulated sine wave, that is very close to and only about 500 Hertz off of the local oscillator frequency. So as a result, what we see are 2 sinusoids, each of those at the same frequency, about 500 Hertz, and 90 degrees offset from each other. And this is what, on a direct conversion receiver, what you would expect to see with a 500 Hertz offset at the input would just be your 500 Hertz tone, and that's often what you'd use to listen for CW. In an SDR receiver, we use Quadrature outputs, get the I and the Q, and that's shown here with these guys 90 degrees out of phase. If I adjust the frequency of my local oscillator in the receiver up and down, I can see that those signals will maintain their 90 degree phase offset relationship, but they're going to stay at that same frequency. Again, identical signals, but 90 degrees out of phase. So that tells us that the Quadrature sampling detector or Quadrature mixer is working, and those low-pass filters are working as well, getting rid of all those those clock feed-throughs and all those other high-frequency artifacts. So that creates these effectively wideband baseband signals that go into the sound card. Okay, little last look at what happens in the receiver as we start changing the input coming in. If I adjust the frequency down, in this case, till I'm very, very close to being zero beated against my local oscillator, these 2 signals are going to be varying very, very slowly in time. Okay, and I can get them moving real slow. Almost looks like just some DC levels that are moving up and down now. We've got the frequency dialed in really close. And that's exactly what you'd expect out of the Quadrature detector. Now in a receiver you might be looking at a modulated signal. Now what happens is with the Quadrature detector, the carrier is removed, and essentially all you're going to be left with is the modulation. So for example, if I turn on some amplitude modulation, now I can just see that amplitude modulation at the output. So this is a 5 kilohertz modulated tone, and we can see every once in a while when I get enough amplitude on channel 2 that I'm reading at about 5 kilohertz there. So now the I and the Q signals, if you're actually going to measure amplitude, you'd actually have to combine the two of them in an RMS fashion, the square root of I squared plus Q squared, and the amplitude in that case would be constant, and we would see just the 5 kilohertz modulation. Well, I hope you enjoyed the walkthrough of the design and signals through this Softrock Ensemble 2 software-defined receiver. Of course, the receiver really works because of all the magic that happens in the software that reads the audio signals coming out, the I and Q signals coming out. The sample rate of the sound card that's used determines essentially how much bandwidth you can see and listen to and tune across in the receiver. And so a higher performance sound card with a higher sample rate will allow you to look at a larger spectrum. So, but it really is a neat little process and an amazingly small amount of circuitry to basically form a really nice, well-performing receiver. I'll try to put some links in the video description, for some background information for the receiver and the Tayloe detector and some of the other topics that are here. And I certainly appreciate you watching and hope you enjoyed this series on this software-defined receiver. See you next time.